Alright, so this is the final exam review, and always in my classes the final exam is optional. So before you run to take the test, you should know whether it makes sense for you to take the test or if you can skip the test. And essentially, if you take the final exam, I drop your lowest tests and put your final exam score in place of the final exam. Let's just say your lowest test score was from chapter 3 and you've got a 63 on it. And then you take the final and you get an 83. What's going to happen is I'm going to drop that 63 and I'm going to replace it with the 83. What that's going to have the effect of doing is it's going to add 20 points to your score, because when I subtract the 63 and add the 83 in, it will have the effect of adding 20 points to your score. So basically, the difference between your final and your lowest test gets added to your total points. If your lowest test is from chapter 6, I'll make it 150 points the final exam, because that test is worth 150 points. So I will, do whatever. If you take the final, I will make it for the test that helps you the most. But the final exam is optional. If you take the final and you do worse than your lowest test score, then I just won't count it. You should know going before you're studying, even studying for the final, if you need to take the final and what you need to get on the final to improve your grade. If you're not sure of what you need to get on the final to improve your grade, then come visit me in my office or shoot me an email. And if I haven't already told you exactly what your grade would be if you're going to skip the final, you should know exactly what you need to get on the final before you take the time to study for it. So shoot me an email if you're not 100% sure of what you would need to get on the final to change your grade. Alright, so I'm going to just jump into this thing. And it could be a two-parter. The final exam is, longish. So questions 1 and 2 want me to find an equation for a line. And to find an equation for a line, what we used was the point slope formula, the y minus y1 equals m times x minus x1 formula. And I'm going to do that for problem 1. In problem 1, I'm going to plug into this formula m equal to 2/3 from the slope. I'm going to plug x1 equal to 6 from the x coordinate of the point that's given. And I'm going to plug in y1 equal to 5 for the y coordinate of the point that's given. That's going to give me y minus 5 equals 2/3 times x minus 6. I'm going to clear the parentheses on the right hand side, and when I clear that parentheses, I'll multiply 2/3 times x and get 2/3 x. And then I'm going to multiply 2/3 times minus 6. I certainly can do that, but if I do 2/3 times minus 6, my calculator tells me that's minus 4. So if you can't do the fraction quickly in your head, just enter it like that. I just entered 2 divided by 3 times negative 6 using the negative in the bottom row of my calculator in the parentheses. So this multiplication is going to give me 2/3 x minus 4. I'll finish the problem by adding 5 to both sides. On the left-hand side, I'm going to wind up having the y isolated, and I need that. On the right-hand side, I have a 2/3 x, and because the numbers have opposite signs, you subtract and take the sign of the larger and get a +1. So I do all the problems on the review, so I'll do every even and odd problem. There won't be a problem for you to practice. So it might be a good idea to actually try to do the review before you watch the video to figure out what you need to study harder on. For question 2, it asks me to find an equation of a line again. It gives me 2 points. I'm going to use this first point for the x1 and y1. So eventually, I'm going to use the y minus y1 equals m times x minus x1 formula. And in for x1, I'm going to plug 3, which is the x-coordinate of the first point given. And for y1, I'm going to plug 1, which is the y-coordinate of the first point given. It turns out that it doesn't matter. If you used x1 equal to 4 and y1 equal to 5 and you use the second point, you'll get exactly the same answer that I get using x1 equal to 3 and y1 equal to 1. On problem 2, I didn't give you the slope, so we have to figure out the slope before we have the number to put in for m into the equation. To find the slope, I'm going to form a fraction, and in the numerator, I'm going to subtract the y-coordinates of the points, which would be 5 minus 1. And in the denominator, I'm going to subtract the x-coordinates of the points, which are 4 minus 3. So for the slope, I'm going to get 4 over 1, which is 4. So on top of putting x1 equal to 3 and y1 equal to 1 into my equation, I'm going to plug m equal to 4 and go y minus 1 equals to 4 times x minus 3. I'm going to clear this parentheses. When I clear that parentheses, I'm going to get y minus 1 equals 4x minus 12. And I'm just going to add 1 to both sides. I'm going to basically have my answer. Or I am going to have my answer. On the left-hand sides, the 1's cancel. I'm left with a y. On the right-hand side, the 4x doesn't change. The numbers have opposite signs, so you subtract and take the sign of the larger and get a minus 11. For questions 3 and 4, they want me to find the x and the y-intercepts if I was to graph this. When I go to answer the intercepts, I should write them as points. And x-intercepts have 0 for the y-coordinate. And y-intercepts have 0 for the x-coordinate. So when I go to write my answer, I should write them as a point. The x-intercept should be a number comma 0. I actually think there's 2 x-intercepts, so I'm going to have 2 points with 0 in the y position. And the y-intercept's going to have a 0 in the x position. Let me do the hard one first. To find the x-intercept, you plug 0 in for y. I'm going to go 0 equals x squared minus 5x minus 6 over x plus 1. That's a tough equation to solve. I'm going to set it up to solve by cross multiplying. I can write the 0 as a fraction by writing it over 1. And that makes it so now I can cross multiply to help myself get an answer for x. When I cross multiply up, I get 1 times x squared minus 5x minus 6. And when I cross multiply down, I get 0 times x plus 1. 2 really easy multiplications. This multiplication just gives you x squared minus 5x minus 6, because 1 times anything is itself. This multiplication gives you 0, because 0 times anything is 0. So I'm going to factor this. This factors into x plus 1 times x minus 6. And to get my x-intercepts, I'll take each factor and set them equal to 0. The factor of x plus 1, when you set it equal to 0, you get x equal to negative 1. The factor of x minus 6, when you set it equal to 0, you get x equal to positive 6. So for my x-intercepts, I'm going to write the point negative 1, 0, and 6, 0. For the y-intercept, you're just going to plug 0 in for x. And there's only going to be one y-intercept for this because it's a function, but in the next one we're going to get 2 y-intercepts. So for the y-intercept, I'm going to go y equals 0 squared minus 5 times 0 minus 6 over 0 plus 1. All the places with zeros just go away and turn into 0. So that's going to leave me with y equals minus 6 over 1. And minus 6 over 1 is equal to minus 6. So for my y-intercept, I'm going to write it as the point 0 minus 6. 4 is a little bit tricky. But it's not ridiculous. So to find the x-intercepts, I'm going to plug 0 in for y. And similarly, to find the y-intercept, I'm going to plug 0 in for x. There's going to wind up being 2 x-intercepts because there's an x squared. And there's going to wind up being 2 y-intercepts because there's a y square. Usually when the letter has a square, you get 2 of that intercept. So my answers for my x-intercepts are going to have some number, and then 0 in the y position. My answer from the y-intercepts are going to have 0 in the x position, then some number. To find the x-intercept, there's going to be two ways to get the intercepts. Either you can factor or square root. So to find the x-intercepts, I'm going to plug 0 in for y and get x squared plus 0 equals to 121. This gives me x squared equals to 121. The safer way to solve this is to set it equal to 0 and solve by factoring, because then you'll get both the x-intercepts and won't make the common mistake that a lot of students might make if they didn't set it equal to 0 and solve by factoring. So this is one way to get the intercept. I set it equal to 0, and now I'm going to factor. This factors into x plus 11 times x minus 11. I have it both factored and set equal to 0, so I'll set each of the factors equal to 0. When you set the x plus 11 factor equal to 0, you get x equal to negative 11. The x minus 11, when you set it equal to 0, gives you x equal to 11. My x-intercepts, it doesn't matter the order that I write them in. One of them's 11, 0. The other one's in negative 11, 0. And it doesn't matter which one you write first or which one you write second. The algebra that I could have done that gives me the intercepts quicker, but you have to be careful, I'll do for the y-intercept. For the y-intercept, I'm going to plug 0 in for x and get 0 squared plus y squared equals to 121. This will give me y squared equals to 121. And I could do exactly the same algebra that I did for the x's. I could set it equal to 0 and do the factoring. The quicker way to do it is to square root plus or minus square root. The danger with solving it by square rooting plus or minus square rooting is if you forget the plus or minus, you'll only get one of the two intercepts. So square rooting cancels out a square. So on the left-hand side, the entire square root symbol and the entire square cancel out, and you're left with a y. On the right-hand side, the plus or minus sign doesn't go away, but the square root of 121 is equal to 11, which I know in my head, but if you didn't know that, you could just go to your calculator and do square root of 121, and it would tell you that it's 11. So I get two y-intercepts, 0 positive 11 and 0 negative 11. Both ways are completely okay to solve for either intercept. Whichever one you find easier, I would do for both. I just wanted to show you both possible ways. This is the quicker way, but so many students forget the plus or minus. But generally, when a problem has a squared, you want to get two solutions. And the only way to get two solutions when you introduce a square root is to have a plus or minus. Problems 5, 6, 7, and 8 give me graphs, and they want me to find the domain and the range. If the graph is a series of scattered points that aren't connected, then the domain and the range are written inside set braces. When the points are connected, you have to write the domain and range in interval notation. But in problem 5, I have 4 distinct points. The domain is going to be the x-coordinates of the points, which are 3, 4, 5, and 7. You don't have to write them in ascending order. You could even write them in a scrambled order. You could say 4, 5, 3, and 7 if you care to. The range from a graph when you have a series of disconnected points are the individual y's. And the individual y's here are negative 1, 2, 2, and 6. When I go to write the range, I'm only going to write 1, 2, even though there's 2 points that have a 2. And I'm just going to put the numbers negative 1, 2, and 6 inside some set braces. That's really the only correct answer for the domain and the range. A lot of times students will feel the urge to connect the points. If the points aren't given to you connected, then they're intended to be not connected. And it'd be wrong to connect them. If the points aren't connected, the domain and the range need to be in set braces, and they need to show the x and the y coordinate of every individual point. For number 6, because the graph is connected, all the points are connected, for the domain and the range, your answer should go in an interval. For the domain, the left edge of my graph has an x coordinate of 0. The right edge of my graph has an x coordinate of 5. I'm going to read from the left edge of the graph to the right edge of the graph and pick off its x coordinates. For the domain, I'm going to say the domain is 0 to 5 because the most left point, its x coordinate is 0. Its most right point, its x coordinate is 5. I put square brackets because all of those are points on the graph. To find the range from this same graph, I need to identify the bottom and the top point and their y's. This point 0, -5 is the bottom point of the graph. The point 3, 4 is the top point of the graph. And when I go to find the range, I write the y-coordinate of the bottom point first, followed by the y-coordinate of the top point. If those points are actually points on the graph, you get square brackets, which I'm going to get here. My range is going to be -5 to 4. This graph I didn't have to extend to find the domain or the range because the first and the last points were marked. In problem 7, the left-hand part of the graph doesn't need to be extended to find the domain and the range, but the right-hand part doesn't need to be extended to find the domain and the range, but the left-hand part needs to be extended all the way to the far left edge of the x-axis and all the way to the bottom of the y-axis. When I go to define the domain, this graph goes to the far left edge of the x-axis, which has an x-coordinate of -infinity, and it stops at that point, which has an x-coordinate of 0. When I go to write the domain, I read from the left edge to the right edge of the graph. Infinities always get round brackets. Points on the graph get square brackets, so the domain would be -infinity to 0. And then when I'm extending this graph, it goes really quickly to the far left edge of my graph and very slowly, but eventually it makes it to the bottom of the y-axis, so the bottom of the graph is going to be at -infinity, and the top of the graph is going to be at this point 0, 2, and its y-coordinate is 2. When I go to write the range, I write the y-coordinate of the bottom of the graph. The bottom of the graph's y is going to be -infinity. Follow it up with the y-coordinate of the top of the graph. The top of the graph has a y-coordinate of 2 because that's a point on the graph. It gets a square bracket. For number 8, when I go to find the domain, I need to extend this graph up and to the right because the right edge isn't labeled. So this graph eventually is going to make it to the far right edge of the x-axis. And I need to extend this graph down and to the left. And beneath the x-axis, it makes it to the far left edge of the x-axis. When I go to write the domain for this graph, because it extends all the way out to the far left and to the far right edge of the graph, I say the domain is negative to positive infinity. When I go to do the range of this graph, I need to figure out the bottom and the top of this graph. And this graph eventually makes it to the bottom of the y-axis, which has a y-coordinate of -infinity, and it goes to the top of the y-axis, which has a y-coordinate of positive infinity. The range of this graph is going to go from the bottom to the top. Round parentheses always on infinities. It's going to be negative to positive infinity. Nine, 10, and 11 ask me to find the domain of 3 different styles of functions. For number 9, to find the domain of a fraction, we ignore the numerator. So in this case, I'm going to ignore the x minus 4, and I'm going to solve the x squared plus 6x minus 7 equal to 0 to get the numbers to exclude from the domain. And once I have those numbers, I'll be able to write my domain in interval notation like it's asked here. So the algebra to find the domain of a fraction is we just set the denominator equal to 0. And in this case, when I set the denominator equal to 0, I factor it. And I set the factors equal to 0. The numbers I'm excluding from the domain are -7 and +1. To figure out how to write my domain properly in interval notation, I'm going to create a number line that has infinities on the edges and the numbers that I'm excluding from the domain written between the infinities, and then I'm going to make the intervals that are implied. The first interval that's implied is the interval from -infinity to -7. The second interval that's implied is -7 to 1. The third is 1 to infinity. I'm just going to write that in my answer. I'm going to put union symbols between those intervals. So the domain of this fraction is from -infinity to -7, and then again from -7 to 1, and then again from 1 to infinity, all round parentheses separated with union symbols. The next two problems are completely different. The technique for finding the domain of a fraction is completely unrelated to finding the domain of a square root, which comes up next. To find the domain of a square root, we just set what's under the radicand, or what's under the radical, and set it greater than or equal to 0. So there isn't any numerator to even ignore. There's no denominator to set equal to 0. To find the domain of a square root, you take the radicand and you set it equal to greater than or equal to 0, and that gives me what the domain is. I just have to make that in interval notation. So the domain is going to be x is greater than or equal to -5. In terms of a number line, that would mean any number starting at -5 and going off forever to infinity. The domain's going to have a square bracket on the -5 because of the or equal to, and it's going to go to infinity, and infinities have round brackets because this is x is greater than or equal to -5 written on a number line. So the domain for problem 10, it would be the interval -5 to infinity. So finding the domain of a fraction is completely unrelated to finding the domain of a square root. But both finding the domain of fractions have algebra to do, domains of square roots have algebra to do. Problem 11 is asking me to find the domain of a polynomial. If it's not a fraction and not a square root and not a logarithm, I guess, the domain is all real numbers. There's no algebra to find this domain, essentially because there's no fraction and no square root. And the domain for this is going to be negative to positive infinity. If you're visual, what's going to happen for these functions? Problem 9, if I went to graph problem 9 that had a domain of these three intervals, at -7 there's going to be a vertical asymptote. At +1 there's going to be a vertical asymptote. And I don't know exactly what the graph's going to do. Let me just graph it real quickly on my calculator with some horrible window. Need to shut my stat plot off that I was using for my last video that I actually did. So if I graph this, the function x minus 4 divided by x squared plus 6x minus 7 and zoom standard it, I'd get a graph that has three pieces. Has this piece, and this piece. And so the graph, it has three chunks. The chunk from -infinity to -7, the chunk from -7 to 1, and the chunk from 1 to infinity. These numbers here show me where the graph has breaks in it. When I go to find the domain, those numbers are where the asymptotes are. In problem 10, if I graph the square root of x plus 5, the graph starts at -5 and goes off to the far right edge of the x-axis, but there's no graph back here. This is why the domain starts at -5, because to the left of -5 on the x-axis there's no graph. And that's why that domain is the way it is. And problem 11, if I graphed it, it wouldn't have any breaks in the graph, nor would it have a starting or stopping point. It's just a generic line like problem 11 that had the domain of negative to positive infinity. So you could actually graph to kind of get a sense if your answers for your domain are right or not. Problem 12, there's no real algebra to do. It asks me to find where a graph is increasing and decreasing and finding some values of maximums and minimums. So when we did this, what we did is on the x-axis we put a negative infinity, a positive infinity, and then the x-coordinate of any turning point. That turning point has an x-coordinate of -3. This turning point has an x-coordinate of -1. And we create intervals. The intervals I'm going to create are negative infinity to -3, all round bracketed for increasing and decreasing, -3 to -1, and -1 to infinity. These points right here are distractor points, have nothing to do with the intervals where the graph is increasing and decreasing. Now in each interval, I move from left to right. In the first interval, as I move from left to right, that's the interval that signifies the portion of the graph beneath the interval negative infinity to -3. As I'm moving from left to right, the graph is getting higher. So I would say the graph is increasing in that interval from negative infinity to -3. Beneath the interval from -3 to 1, the graph is getting lower as I move from left to right. So in that interval from -3 to -1, the graph is decreasing in that interval. And in the last interval, the interval -1 to infinity, the portion of the graph that I see within that interval, as I move from left to right, the graph is going higher. So that's going to be another increasing interval. And when you have two intervals that do the same thing, you separate them with a union. This point -3, -8's a maximum point, and Part C wants the x-coordinate where the function has a local maximum. That's going to be that hump right there. It's going to be x equal -3. Then it wants the local maximum value. The local maximum value is going to be the y-coordinate, which is going to be y equal to -8. And then part E wants the x-coordinate of the local minimum. This point down here, that little low point, is a local minimum point. Its x-coordinate is x equal to -1, and its y-coordinate goes into part F. The local minimum value is that y-coordinate. You might not even be able to read it anymore, but it's y equal to -12. That's a bunch of parts, which could be, as many as 10, 15 points. Well, there's 1, 2, 3, 4, 5, 6, at least 12 points on the final exam, maybe even a little bit more for no algebra. (13) wants me to find an average rate of change. Problem 12, you're going to see if you take brief calculus or regular calculus a bunch. Problem 13, if you take brief or regular calculus, you're going to see it right at the beginning of class. An average rate of a change is a slope of a line that connects 2 points. So when I'm asked to find the average rate of change, I'm really being asked to find the slope of a line that connects 2 points on the graph. And the 0 and 2 that are given in this problem are the x-coordinates for each of the 2 points that I need to find the slope of between. I need to get the y-coordinates. The first y-coordinate I'm going to get by plugging in 0 for x. And I'm going to go 0 cubed plus 6 times 0 squared. And that's going to give me 0. So one of the 2 points that I'm going to use to find the slope of the line between those 2 points is 0, 0. The second point, I'm going to plug in 2 for x and get 2 cubed plus 6 times 2 squared. I think that's 32. If I did it on my main screen of my calculator, I could just go 2 cubed plus 6 times 2 squared. I wrote a 4 there for some horrible reason. So I get f of 2 equals to 32. So the 2 points that are implied by these x-coordinates are the points 0, 0 and 232. So the average rate of change is going to equal 32 over 2 minus 0. So it's going to be 32 over 2, which is 16. So the answer to 13, the average rate of change is going to be 16. 14, we did a bunch of these this semester. It gives me the function f of x equals to x squared. It wants me to find f of x plus 2 minus 4. Because the x plus 2 is in a parentheses, it needs to go in a parentheses with the exponent of 2 outside of it. And the minus 4, because it's not in a parentheses, it's going to be after the function. For part B, to describe how it moves, a plus inside a parentheses is going to move it to the left. The minus after the function is going to move it down. So we did this like 4 times this semester, so hopefully you're good with that. I was going to flash that sheet up here, but that's something you should know by now, the left, right, ups and downs. If not, I forget when we did it the first time. Shoot me an email. I can tell you right where that sheet is at. I think it's like 3.5. 15 gives me the function g of x equals the square root of x. It wants me to find negative g of x minus 3 minus 5. The negative, because it's written in front of the g, is going to get written in front of the square root when I go to find each function. That's going to reflect the graph over the x-axis. When I go to describe what the graph gets done, that negative reflects the graph over the x-axis. The x minus 3 part of this, because it's in a parentheses, is going to go under the radical. That's going to shift the graph right 3 units. The minus 5, because it's not in a parentheses, goes after the function, and it's going to move the graph down 5 units. So to find each function, you're going to have a negative, then the square root of x minus 3, and then minus 5. And then you need, in any order, say it's reflected over the x-axis, shifted right 3 and down 5. (16) gives me h of x equals the absolute value of x. First, I need to find h of x minus 3 plus 4. Because a minus is inside the parentheses, it's going to wind up going under the absolute value. The absolute value is working like the parentheses in this problem when I'm going to find each function. And the plus 4 is going to go afterwards. The minus inside the absolute value is going to shift the graph to the right 3 units. The plus after the function is going to move the graph up 4 units. And this is kind of how I write my answers, real primitively. I don't take the time to write a lot of words in my answer for these shiftings. All right, 17 gives me a function f of x equals x squared. It first wants me to find f of x minus 3 plus 4, and f of x minus 3 plus 4. The x minus 3 is going to go in a parentheses with a squared outside of it. So that's finding the function. To describe the transformation, it's going to shift it right 3 for that, and up 4 for that. I'm going to use my calculator to get a table of values. When we go to do a table of values, we need to have the vertex kind of in my table. And what I'm going to do to figure out to get my table started, the number that's going to go in the middle of my x column, I get by taking the inside of the parentheses and setting it equal to 0. So the parentheses there has an x minus 3. If I set that equal to 0, I'll get x equal to 3. When I go to do my table, I'm going to wind up having 5 values in the x column. 3 is going to be in the middle, and then I'm going to go smaller than 3 and bigger than 3. And I'm going to graph the function that has the points, the x coordinates 1, 2, 3, 4, and 5. And I'm going to use my calculator to get the y coordinates. So I'm going to go y equals clear, parentheses, x minus 3 squared plus 4, and I'll graph it, but I want to get a table, and I'm going to go second table and just find, I'm way off, I'm at 23 for whatever reason. My calculator is way away from the table, but I can arrow down and find those. So the first point I'm going to write is the point 1, 8. The second point I'm going to write is the point 2, 5, just stealing from my table on my calculator, then 3, 4, 4, 5, and 5, 8. You can tell you have a decent table if the y's repeat. If the y's don't repeat, you're not going to get a very good graph of a parabola. So now I'm going to graph this real primitively. So I need 1, 2, 3, 4, and 5. I don't know if I left myself room to get up to 8, so I'm going to increment by 2. So 2, 4, 6, and 8. And now I'm just going to plot the points and make a U that looks just like my calculator's graph, or more or less like my calculator's graph. So the point 1, 8, 2, 5, 3, 4, 4, 5, and 5, 8. Alright, so it looks just like that. Done with part B. Now I'm going to go to find the domain in the range. This graph, when I go to find the domain, if I extend it up and to the right forever, it's eventually going to make it to the far right edge of the x-axis. Similarly, if I make it go up and to the left forever, eventually it's going to go to the far left edge of the x-axis. Because this is a polynomial, though the domain of all polynomials is negative to positive infinity. So the domain for this graph is going to be negative to positive infinity. When I go to do the range of this graph, I have to nail the bottom point and the top point in terms of their y's. This vertex is the bottom point, and its y-coordinate is 4. The graph goes up to the top of the y-axis, so there's a y-coordinate of infinity. For the range, I'm going to read from the bottom to the top along the y-axis. I'm going to say the range goes from y equal to 4 to y equal infinity. Infinities always get round brackets. Numbers get square brackets if they're from points on the graph, and that vertex is a point on the graph. Should I get a square bracket? For the increasing and decreasing, I already have the infinities on my x-axis. I also need to put a 3, the x-coordinate of that turning point, on my x-axis. And I'm going to create two intervals. I'm going to create an interval from negative infinity to 3 and an interval from 3 to infinity to figure out where the graph is increasing and decreasing. For the first interval, that interval from negative infinity to 3 represents that portion of the graph, and that portion of the graph as I'm moving from left to right is getting lower. So I'm going to say the graph is decreasing in that first interval that I wrote, negative infinity to positive 3. The portion of the graph that corresponds to the interval 3 to infinity is this portion of the graph. And as I'm drawing that, my pencil or my marker is going higher. So that means that interval corresponds to a part of the graph where the graph is increasing. So I'm going to say it's increasing from 3 to infinity. State if the function has a local maximum. If it has a local maximum, state the local maximum value. The only turning point here is a minimum point, so it doesn't have any. So it doesn't have a local maximum. I'm just going to write none for that. Or it doesn't have a local maximum. It has a local minimum. It has a local minimum. We should say probably at x equal to 3. And the local minimum value is the y-coordinate of that point, which is 5. So it says state if the function has a local minimum. It does have a local minimum. It has a local minimum, and the x-coordinate is 3. And the local minimum value is the y-coordinate of that minimum point. And that y value is the y value of the vertex is 4. So that's everything for problem 17. That's another 1, 2, 3, 4, 5, 6, 7-part problem. That's probably at least 14 points on the test. So 18 wants me to start off using synthetic division to factor a polynomial. To do synthetic division in 18a, I need to write a backwards L and a line kind of next to it, and the coefficients of the problem, which are 1, 1, 2, and 2 above that horizontal line. Then I need to sketch a graph and find an x-intercept of this function to get started with this. So I'm going to graph this function, y equals x cubed plus x squared plus 2x plus 2. Graph it. See if I can find an x-intercept. Looks like there's an x-intercept at x equal to -1. Let me check on the table to make sure that's the case. X-intercepts have zeros in the y-coordinates. So there's an x-intercept at x equal to -1, and I'm going to use that for my synthetic division, and I'm going to use that in my factoring, because when I'm asked to factor this, if you have an x-intercept of an x equal to -1, then you're going to have a factor of x plus 1. So when I go to factor this to write my answer to part A, one of the factors is going to be x plus 1. The other factors I'm going to get when I finish up my synthetic division. To do synthetic division, first we bring the number down, and then we're going to multiply and add. -1 times +1 is -1. I would add these, but they have opposite signs, so I subtract them. 1 plus -1 is 0. Then -1 times 0 is 0. 2 plus 0 is 2. -1 times 2 is -2. 2 plus -2 is 0. This is whatever this answer is going to go as a factor after that x plus 1. I'm going to start putting x's into this problem 1 power less than the problem had. The problem started with an x cubed, so this is going to signify a 1x squared. No sign there, so I need a plus. This 0 is going to have an x next to it. No sign there, so I get a plus. I'm done with x's. The 2 is going to be the constant, and the 1 is going to be the remainder. So next to my factor of x plus 1 that the x-intercept gave me, I'm going to write a factor of x squared plus 2. X squared plus 2 is prime because it's a sum of squares. So this is as far as 18a factors, and this is considered completely factored, and this is actually my answer to 18a. This is how the polynomial that's given factors. When I move on to part B, I need to set the problem equal to 0 and solve for x. And to solve for x, you usually factor, and then you set the factors equal to 0. So to solve x cubed plus x squared plus 2x plus 2 equal to 0, I'll factor that, and then I'll set each factor equal to 0. So I'll set x plus 1 equal to 0, and x squared plus 2 equal to 0. X squared plus 1, x plus 1 equal to 0 gives me an answer of x equal to -1. X squared plus 2 equal to 0, I'm going to get an answer by square rooting like I did when I found that y-intercept. When I introduce a square root into a problem, I have to plus or minus that square root. This is going to give me x equals plus or minus the square root of -2. And of course, anytime you have a negative under a square root, you can make that negative an I outside of the square root. So this problem in part B has 3 answers. When I go to answer 18b, I'm going to say the answers are x equal to -1 and plus or minus the square root of 2 times I. Here we have a couple graphs to do. And we ask a bunch of questions about the graph, and then you just sketch it by hand. So 19 gives me the function, I don't know how readable that is. It gives me the function f of x equals 2x plus 6 over x minus 3. To find the domain for part A, we're just going to ignore the numerator and set the denominator equal to 0. So I'm going to go x minus 3 equal to 0. That's going to give me x equal to 3. I'm going to create a number line to help myself find the domain. I'm going to put infinities on the left edge and the right edge of the number line, and the number I'm excluding from the domain between them. And then I'm going to create round brackets and make intervals. My domain to this function is going to be the interval from -infinity to 3, and then again the interval from 3 to infinity. The algebra for finding the domain gives you the vertical asymptote for all the problems that we're going to get in our final. So we're going to get x equal to 3. So for part B, there's no extra work. The vertical asymptote is just comes out to the work for part A. For part C, the horizontal asymptote, I had to pause the video and print something out. The horizontal asymptote is hinged on how the exponent, the highest exponent, compares to the highest exponent in the numerator compares to the highest exponent in the denominator. This is a case where the highest exponent in the numerator and the highest exponent in the denominator are both 1. So if I look at the numerator, it's 2x to the first plus 6 over 1x to the first minus 3. The highest exponent in the numerator is 1. The highest exponent in the denominator is 1. The horizontal asymptote is y equal to the coefficients of those numbers divided by. So the horizontal asymptote is going to be y equals 2 over 1 because it's when the highest exponents are tied between the numerator and the denominator, the horizontal asymptote is y equals, and you divide the coefficient of those highest power terms. So the horizontal asymptote for problem part C is going to be y equals to 2 over 1 or y equal to 2. You can't have both a horizontal and a slant asymptote. You get a slant asymptote if the highest exponent in the numerator is bigger than the highest exponent in the denominator. For the x-intercepts, I'm just going to set the whole function equal to 0. So I'm going to go 2x plus 6 over x minus 3 equals to 0. I'll get ready to cross multiply by writing it as 0 over 1. I'm going to cross multiply up and down. When I cross multiply up, I get 1 times 2x plus 6. When I cross multiply down, I get 0 times x minus 3. This is going to give me 2x plus 6 equals to 0. I'll minus 6 from both sides and get 2x equal to minus 6. I'll divide both sides by 2 and get x equal to minus 3. So my x-intercept is going to be the point -3, 0. I'll try to squeeze the y-intercept on this page. For the y-intercept for part E, the y-intercept, you just plug in zeros for the x's. So I'm going to go f of 0 equals 2 times 0 plus 6 over 0 minus 3. That's going to be 6 over minus 3, which is minus 2. For the y-intercept, it's going to be the point 0 minus 2. When we get to the test, you're going to be given a blank graph to do part F that has the window implied on it. I didn't think to do that today. So I'm going to hope a Zoom standard is going to work fine when I go to graph this. So now I'm going to do part F and sketch a graph. And on my graph, I need to show all these features. The first feature I need to show is the vertical asymptote at x equal to 3. So I'm going to draw a dashed vertical line through 3 on the x-axis for the vertical asymptote. I also need a horizontal asymptote at y equal to 2. So I'm going to draw a dashed vertical line through 2 on the y-axis. I need an x-intercept marked at the point -3, 0. And a y-intercept marked at the point 0, -2. That's all I can do with my parts A through E. That's all the information that I have that's graphable. So now I'm going to graph this. And I'm going to use a standard window because I didn't take the time to tell you what window is going to make sense. So let me try to enter this at, so y equals clear, parentheses 2x plus 6 divided by parentheses x minus 3 in Zoom standard. And hopefully I get something that's reasonable. Seems reasonable enough. Remember, if we want to get the asymptotes in, the horizontal asymptote's easy. To get the horizontal asymptote at 2, I can just type in y equal to 2. There's my horizontal asymptote. That looks reasonable. To get the vertical asymptote in, I'll take 1,000 times the denominator, or the factor that made that. So if I want to see the vertical asymptote, I'll go 1,000. And then the denominator, or the factor that made that vertical asymptote, with x minus 3. Now when I hit graph, I'll see something that mimics a vertical asymptote. And now I'm just going to basically copy this. So I'm going to make a upper right-hand corner that kind of goes towards the asymptotes, and a bottom left-hand corner that goes through the intercepts and towards the asymptotes. It's got to go through the intercepts. And that seems reasonable. Again, it's a reasonable copy of what I see here on my screen, so I feel good about that graph. And I'll move on to do question 20. In question 20, it looks like I have to do negative 15 to 15 for my window. I have an answer here, but I didn't take the time to make my graph easy for you to follow. Sorry about that. So for problem 20, the first thing I'm going to do is find the domain. To find the domain of a fraction, we're going to ignore the numerator and set the denominator equal to 0. The denominator is x squared plus 4x minus 21. I'm going to set it equal to 0. I'm going to solve by factoring. To find out what the domain is, I'm going to put infinities on the edges of a number line and the numbers that I'm excluding from the domain between the infinities, and create the intervals that are implied. My domain's going to have three intervals: an interval from negative infinity to negative 7, and then an interval from negative 7 to 3, and then an interval from 3 to infinity. There's no extra algebra for part B. You get vertical asymptotes where you have breaks in the domain unless it's a special hole that we didn't do any of. So we're going to get vertical asymptotes where we have breaks in the domain. For part C says if the exponent in the highest exponent in the numerator is less than the highest exponent in the denominator. In this particular problem, the x in the numerator with the highest exponent is x to the first. The x in the denominator with the highest exponent is x to the second. If the highest exponent in the numerator is less than the highest exponent in the denominator, then the x-axis, which has the equation y equal to 0, is a horizontal asymptote. There's no algebra to do for that. So for part C, the horizontal asymptote is y equal to 0. That just comes from knowing that fact. And there's going to be no slant asymptotes on the test, so you just have to remember these two applications that I just did one of each. All right, so for 20 part D, to find the x-intercepts, we take the whole function and set it equal to 0. I write that as 0 over 1, and I cross multiply. When I cross multiply down, I get 1 times x minus 1. When I cross multiply up, I get 0 times x squared plus 4x minus 21. This is going to give me x minus 1 equals to 0, because 1 times anything is itself, 0 times anything is 0. This is going to give me x equal to 1. When I go to write the x-intercept, I'm going to write it as the point 1, 0. And then I've got a nasty, nasty y-intercept. When I go to do 21e, I'm going to find f of 0, which is going to be 0 minus 1 over 0 squared plus 4 times 0 minus 21. It's hardly readable. All these pieces go away. This piece was actually a 4 times 0. That goes away. And that piece is a minus 21. That doesn't go away. What doesn't cancel is the minus 1 in the numerator and the minus 21 in the denominator. The double negative is going to turn to a positive. The y part of the y-intercept is 1 over 21, which is really going to be close to the origin. All right, so done with all the algebra I could do without my calculator. And the best I can tell, I need to have, I'm going to draw something like you're going to get on the test. So on the test, if this was the test question, you're going to be given a blank graph that has numbers on the axis, and the numbers I put on the x-axis go from negative to positive 14, and the numbers I put on the y-axis go from negative 4 to 4. I probably just played around a little bit and decided that those I can see all the features of the graph. So now I'm going to start drawing all the features that I need to draw. The first features I'm going to draw are the asymptotes at x equal to negative 7 and x equals to positive 3. So through negative 7 on the x-axis, I'm going to draw a dashed vertical line. And through 3 on the x-axis, I'm going to draw a dashed vertical line. To get this drawn on my calculator, I have to enter y equals 1,000 times x plus 7. To get this drawn on my calculator, I'm going to enter y whatever equal to something times x minus 3. That's on my calculator to make those show up. The horizontal asymptote at y equal to 0 is just right on the axis. I won't even be able to get my calculator to show that because it's going to draw the axis and it's not doing multiple colors to make anything look different. So that I won't be able to see. I'll be able to see it, but I won't be able to draw it separately. For the x-intercept at 1, 0, that's about right there. And 0, 1 over 121 for the y-intercept is just barely above the origin. So those are all the features that I can plug in. And now I'm going to get my calculator to graph. So I'm going to set my window up. I'm going to go from negative 14 to 14 on the x's and negative 4 to 4 on the y's. Now I'm going to enter the function, clear out all this junk. Parentheses x minus 1 divided by parentheses x squared plus 4x minus 21. When I graph it, it's not going to show the asymptotes. That doesn't really bother me so much. If you want to see the asymptotes, we just need to plug them in here. I'm going to go y equals then 1,000 times x plus 7 to see the left one, and 1,000 times x minus 3 to see the right one. Sometimes the graph gets ugly when you see the asymptotes, but there's the asymptotes drawn in for me. Now I'm going to copy a left-hand corner, a middle piece that goes through the intercepts, and a right-hand piece. You can barely see these pieces. The right-hand piece goes right through here. It goes right close to the vertical asymptote and right to the horizontal asymptote. Let me take these asymptotes off because I think they're messing up the graph more than they're helping. So the right-hand piece I drew. The left-hand piece is easy enough too. It's going to be just down here. And this middle piece just has to go through the intercepts and just kind of snakes towards the asymptotes. It crosses the horizontal asymptote. That's legal to do. So it's going to go something like this. Goes through the y-intercept, the x-intercept, and works its way down. Probably can put little arrows at the ends of each of these, but I don't really have to. But my graph feels good. It goes towards all the asymptotes in a reasonable direction, goes through the intercepts. So I feel good about my graph, and this is probably a good place to stop to go between a part 1 and a part 2. So we'll just stop right now, and if you feel motivated, keep going. If not, take a break.